Hello and welcome. In this lecture, we will discuss some of the problems and their solutions with respect to the chapter functions and relations. In this problem, we are given a set A having elements 1 and 2 and set B having elements 2 and 3. We are required to find the number of subsets of A cross B. The number of elements in set A is 2 and the number of elements in set B is also 2. Therefore, the number of elements in the Cartesian products of A and B is equal to 2 cross 2. This is equal to 4. Therefore, the number of subsets of A cross B is equal to number of elements in the power set of A cross B. This is equal to 2 to the power 4 and this is equal to 16. Therefore, the number of subsets of A cross B is 16. In this problem, it is given that the Cartesian product of an unknown set A with itself has 9 elements. Two of them are -1, 0 and 0, 1. We are required to find the unknown set A. So we are given that n of A cross A is 9, which can be written as 3 times 3. We also know that the number of elements in the Cartesian product of A and B is equal to the number of elements in A times number of elements in B. Therefore, the number of elements in A cross A will be equal to number of elements in A times number of elements in A. Therefore, the number of elements in A will be 3. Since the elements of the pair -1, 0 and 0, 1 are from set A itself and the number of elements in the set is 3, the elements of the set are -1, 0 and 1. Therefore, A is the set of elements -1, 0 and 1. In this problem, we are given a set A of natural numbers from 1 to 9 and we are required to define a relationship R from A to A having elements x, y such that 3x is equal to y and x, y is in set A. Since the second element of the ordered pairs is 3 times the first element, we have the relationship from A to A as having elements 1, 3, 2, 6, 3, 9. We can show this relationship graphically as follows. So we take R from A to A and the element 1 is related to element 3 and we have a second pair of element 2 and 6 and we have a third pair of element 3 and 9. In this problem, we are given a set A having elements 2, 3, 4, 5, 6 and we are given that R from A to A is a set of pair of elements A, B such that A, B is in A and B is divisible by A. We are required to find elements of R and its domain and range. As per the problem, element B of the pair A, B is a multiple of A. Therefore, only possible pairs are 2, 2, 2, 4, 2, 6, 3, 3, 3, 6. Therefore, R is a set of pairs 2, 2, 2, 4, 2, 6, 3, 3, 3, 6. Now the domain of this R is the set of first elements of each of the pair and the range is the set of second elements. Therefore, domain is set of elements 2, 3 and range is the set of elements 2, 3, 4, 6. Therefore, domain is the set of elements 2, 3 and range is the set of elements 2, 3, 4, 6. In this problem, we are given two relations A and B and we are required to determine if they are functions. For a relation to be a function, the elements of the domain shall have only one image in range. A is a set of pairs of elements 2, 1, 5, 1, 8, 1, 11, 1, 14, 1. The domain of A is set of elements 2, 5, 8, 11 and 14 and the range is set of element 1. Since every element in the domain have only one image in range, A is a function. Now B is a set of pairs of elements 1, 2, 1, 5, 2, 5. Domain of B is set of elements 1 and 5 and range is set of elements 2, 5. Here we can see the element 1 in the domain have two images. One image is 2 and the other image is 5. Since every element in the domain does not have one image in range, B is not a function. In this problem, we are given a function fx is equal to square root of 9 minus x square. We are required to find the domain and range of this function. For this function to have a real value, the expression inside the square root shall have positive value. Therefore, 9 minus x square shall be greater than or equal to 0. This means that x square shall be less than or equal to 9. This means that x shall be greater than or equal to minus 3 and it shall be less than or equal to 3. Therefore, x is in the closed interval minus 3, 3. Now fx is maximum when x equals to 0. The maximum value of fx is 3 and fx is minimum when x is equal to minus 3 or 3. The minimum value of fx is 0. Therefore, domain is equal to closed interval minus 3, 3 and range is equal to closed interval 0, 3. In this problem, we are given a function fx is equal to 2 minus 3x, where x is a real number greater than 0. So we are given that the domain of fx is all real numbers greater than 0. The fx will be minimum when x is maximum. Therefore, f of infinity is equal to minus infinity. Fx will be maximum when x is minimum, therefore f of 0 is 2. Therefore, range of fx is the upper interval minus infinity to 2. In this problem, we are given a function fx which takes on the value x square when x is greater than or equal to 0 and less than or equal to 2, and it takes the value 3x when x is greater than or equal to 2 and less than or equal to 10. We are required to check whether fx is a function. We can see that when x is equal to 2, this function has two values and we have to check whether these two values are same. Therefore, the value of this function when x is equal to 2 is 2 square and 3 2 and this is equal to 4 and 6. Therefore, we see that the value 2 does not have a unique image in the range and therefore this is not a function. In this problem, we are given a function fx is equal to x square plus 2x plus 1 divided by x square minus 8x plus 16 and we are required to find the domain of this function. We can write this function as the ratio of two functions fx equal to ux by vx where ux is equal to x square plus 2x plus 1 and vx is equal to x square minus 8x plus 16. For fx to be real valued, vx shall not be 0. This means that x square minus 8x plus 16 shall not be equal to 0. This means that x square minus 2 into 4x plus 16 shall not be equal to 0, and this means that x minus 4 square shall not be equal to 0, and this means the value of x shall not be equal to 4. Therefore, the domain of fx is all values in R minus the element 4. In this problem, we are given a function which is equals to the modulus of 2x minus 3, and we are required the domain and range of this function. Since this is a modulus function and the domain of a modulus function is all the real values of x, therefore domain of fx is also minus infinity to infinity. The range of any modulus function is positive real numbers. Therefore, the range of fx is also 0 to infinity. Therefore, domain of fx is real numbers from minus infinity to infinity, and the range of fx is real numbers from 0 to infinity. In this problem, we are given a function fx equal to x square by x square plus 1 for all real values of x. We are required to find the range of this function. For the solution of this problem, we will assume another function gx which is inverse of fx. That means gx is equal to 1 by fx. This means that gx is equal to x square plus 1 by x square. This means gx is equal to 1 plus 1 by x square. Now, if x is very close to minus infinity or plus infinity, x square will be very close to plus infinity. And if x square is close to plus infinity, 1 by x square will be tending to 0. That means gx will be approximately 1. Now, if gx is approximately 1, f of x, which is equal to 1 by gx, will also be approximately equal to 1. Also, from this function we can see that if x equals to 0, f of x will be equals to 0. Therefore, the range of this function fx equal to x square by x square plus 1 is the interval 0, 1, which is closed in 0 and open in 1. In this problem, we are given a relation R having set of elements a comma b such that a and b are in natural numbers and a is equal to b square. We are required to check which of the following statements are true. The first statement says that a comma a is in R for all values of a belonging to natural numbers. If a comma a is in R, this means that a is equal to a square, which is not possible except for a equals to 1. Therefore, a comma a is not in R for all values of a belonging to natural numbers. The second statement says that if a comma b is in R, this implies that b comma a is also in R. Now, if a comma b is in R, this means that a is equal to b square, and b comma a in R means that b is equal to a square, which is again not possible except when a is equal to b is equal to 1. Therefore, a comma b in R does not imply that b comma a is also in R. The statement in part 3 of this problem is that if a comma b is in R and b comma c is in R, this implies that a comma c is in R, and we have to check whether this statement is true. Now for a comma b to be in R, this means that a is equal to b square, and if b comma c is in R, this means that b is equal to c square. Now for a comma c to be in R, it is required that a is equal to c square. Now since a is equal to b square and also since a is equal to c square, this means that b square is equal to c square, which is again not possible except for a is equal to b is equal to c is equal to 1. Therefore, if a comma b is in R and b comma c is in R, this does not imply that a comma c is in R. If we denote integer numbers by z, in this problem we are given a relation f to be a subset of z cross z, which is defined by f equals to ab comma a plus b, where a and b are integers. We are required to find if f is a function from z to z. Now we are given that f is equal to ab comma a plus b for a and b in z. The domain of f is ab, where a and b are integers, and the range of f is a plus b, where a and b are also integers. For f to be a function, every element in the domain must have a unique image in the range. Therefore, AB must be unique for all values of A and B. Since a compound number can be formed in more than one ways, AB cannot be a unique number. For example, the number 12 can be formed by the product of 3 and 4, and it can also be formed by the product of 2 and 6. Therefore, the image of 12 in the range will be 3 plus 4 equals to 7 and 2 plus 6 equals to 8. This means that 12 does not have a unique image in the range. Therefore, every element in the domain of f does not have a unique image in the range. Therefore, f equals to ab comma a plus b, where a and b are integers, is not a function. In this problem, we are given two functions f and g operating on real values of x, defined by fx equals to x minus 1 and gx equals to 2x plus 3. We are required to find their addition, their subtraction, their multiplication, and their quotient. So we are given that fx is equal to x minus 1 and gx is equal to 2x plus 3. Therefore, f plus g of x is equal to f of x plus g of x. This is equals to x minus 1 plus 2x plus 3. This will become 3x plus 2. Further, f minus g of x will be f of x minus g of x, which will be equal to x minus 1 minus 2x minus 3, and which will be equal to minus x minus 4. Fg of x will be equal to f of x times g of x. This will be equal to x minus 1 times 2x plus 3, which will become 2x square plus x minus 3. And the quotient f by g of x will be f of x divided by g of x, which will be equal to x minus 1 divided by 2x plus 3, provided that 2x plus 3 is not equal to 0 or x is not equal to minus 3 by 2.